This is Himabindu from the IARE college. So today in this video I would like to explain about the pumping lemma concept in the theory of computation. So what is meant by pumping lemma and where we are going to use and how many types of languages we are going to use this pumping lemma we will discuss in this video. So coming to the introduction to the pumping lemma, so what is meant by pumping lemma and which type of languages we are going to use this pumping lemma concept. So according to the pigeonhole concept, we are using the pumping lemma concept to derive that the language which are not regular, which are regular or irregular, we need to test according to the pumping lemma concept, and then we can decide whether the language belongs to a regular or not. So here the language accepted by the finite automata. So we already know that what is meant by regular languages. So the language which is accepted by the finite automata is known as the regular languages. So and we also discussed about the how many types of languages we have in a theory of computation. So how many types of languages? Let me briefly explain the number of languages we have in the theory of computation. First one is regular language. So regular languages which we can construct a finite automata with the regular languages, and this is a subset of context free language. So context free language which is used to generate the push down automata missions. The language which is used to construct a mission called push down automata is known as the context free language. And coming to the context sensitive language. So context sensitive language which is a subset of language recursive enumerable languages. So this is a recursive enumerable languages, or we can write. So these are all the different types of languages. So in these languages, in the theory of computation, we have different types of languages, 4 types of languages. So in this one, which type of languages we are going to use this pumping lemma concept? So the pumping lemma which is used, 2 words we have, the pumping and lemma. So what is this pumping? The word pumping refers to generating many input strings by pushing a symbol into a input string repeatedly. So whenever we additionally add the pumping length to the given string, so if it is generating again the same language, then it is saying that by using the pumping lemma concept, the language is proven as a regular language. And if it is not equal to the language, equal to the string what we have generated, which is already we have the language strings, which if you compare both the 2 strings, if it is not equal number of string length is there, or equal number of pattern is not there, then we can say that it is a non-regular language. So this pumping lemma concept which is a negative test. So it is a negative test for the languages which is regular or not. And here where we are using this pumping lemma concept, there are 2 pumping lemmas. One is regular languages and for context free languages. We have 2 types of pumping lemma. One is for regular languages, and here we have seen the languages, number of languages. In this number of languages, regular language we are going to use this pumping lemma concept. And for context free language also we are going to use the pumping lemma concept. So these 2 languages which are going to be taken for the language test, whether the language belongs to the particular regular language or context free language. And for this one we have a statement and we have some conditions in the pumping lemma concept. We will discuss in the coming slides. So here what is the statement, what is the theorem says that the language, if the language is regular, so language, if we take a regular language, so now we are talking, we have 2 types of pumping lemma we discussed, right? So in this one, first we will take the regular language pumping lemma. So regular language pumping lemma, then we will talk about the context free languages. And here before going to the before going to the pumping lemma concept, so let me write the brief pumping lemma concept. So pumping lemma is, I'm describing it as a PL. So pumping lemma is a negative test. It is a negative test. So negative test for the languages. So negative, it is pumping lemma is a negative test for the languages. And here, if you have a language, so a many number of languages we have. We have a regular language and context free language. Whatever we have, the language, whether it is regular or irregular, we will take the number of languages and we apply pumping lemma pumping lemma, and we will get the result as pass or fail. So here, if we give one test to the language, it will result as a two things. One is a true or false, or it is pass or fail. So in this one, pass means, so we can say that the pumping lemma test is passed, in the sense we can say that it is a regular language. And if it is fail means, we can say that it is a non-regular languages. So here, these are the two situations we got from the test results. So here, if we pass the pumping lemma test, we can say that it is a regular language. And if we fail in the pumping lemma test, we can say that it is a non-regular languages. But here, we can't say that if all the pumping lemma test passed results can be clarified as a regular languages. So we have a regular languages here. If we got the past result, we can't say that it is a particularly regular languages. So that's why we have to name as, so if we pass the test, so PL is a pumping test and pumping lemma test, and pass the result, if we got the result as a pass, so we can say that it is a regular, and we can also say that it is undecidable. And here we got the result as a fail, we can say that it is a non-regular. And we also say that it is surely it is a decidable language. Decidable, unregular. So these are the two differences. When we got the result as a positive, we can't say that it is a particularly regular test, a regular language. And if we got the result as a failure, we can damn surely, and we can surely say that it is a non-regular languages. So these are the pumping lemma concept. And with coming to the statement of the pumping lemma, so here when we are talking about the regular languages, so pumping lemma for the regular languages, we have the statement called, if L is a regular language, we have to take one language here and we have to apply the pumping lemma test. So here we have to take the language L and then pumping length P. So P, we have to pumping length, we need to give the pumping length for the language such that any string S where, so S means the string. If suppose here the language which is having the strings like AA and BB and AA, EBB and this so on, if we are having the language this kind of strings, so we individually we need to take one string, so that the string which is what we are taking pumping length, so the value of the P should be greater than or equal to P. The string, suppose here the P is 3, if you take P is 3 and we need to take this kind of languages. Why? Because 3 less than or greater than or equal to 4 here. So this is the length. So length of the string is here 4. So the string what we are taking for the pumping lemma test is the statement we need to follow this one. So pumping length P, which is we are taking, and the string, we need to choose one string from the language. That string is following this condition. So what is the string? The mod of S. The mod of S is nothing but the length of the string and is greater than or equal to P. So may be divided into 3 parts. So, and this is for only choosing the string from the language, given language. So here we took the language, we assumed the language L, and in that one we took the string based on this condition, and that string is divided into 3 parts. So what are the 3 parts? X, Y, Z, and the string is going to be divided into 3 parts, and the 3 parts are also we need to follow this condition. So first one is X, Y power I, Z belongs to language. So we need to assume that. So we need to assume this language which is particularly belongs to the regular language, and we need to follow the second rule, the length. So while dividing the string into 3 parts, so we need to follow this condition. So here y, the length of y is greater than 0. So here we need to check this condition while dividing the 3 values, x, y, z values. So here y is greater than 0. And here xy, when we combine the length of xy values, we will get the result greater than, less than or equal to p. So what we have taken here 3 as a p length, and if you combine these two, whether it is equal to or less than p. And these 3 conditions we need to follow for the pumping lemma concept. And while dividing the string into 3 parts, we need to follow, must and should follow these 3 conditions. And in simple words, if a string y is pumped here, so y we need to in the middle of, we have divided the string into 3 parts. In that one, we need to take the y value and we need to pump the value. So that pumping value, it should be a y, or insert any number of times. We need to repeat the y value. So that repeating iteration is nothing but represented as a y power I. So this I value should be greater than or equal to 0. So greater than or equal to 0. We need to follow this condition while repeating the I value. So, and then we need to pump the pumping lemma. So pumping lemma is used to prove that irregularity. So as we already discussed, so this pumping lemma is a negative test, and with this only we can prove that it is a irregular. And with this pumping lemma, we can't say that when it is test result as a positive, we can't say that it is particularly a regular language. So it is a negative test only to represent it is not a regular language. So that is the pumping lemma concept, and it means that if a language is a regular, it always satisfy the pumping lemma. So if it is regular, we can always satisfy this pumping lemma concept. And if at least one string is made from pumping, so one string one string we need to pump the value, or y value we need to pump, and then we got the result as the same what we have already have the language strings when it is compared. So if it is additionally any pattern or any length is added to the strings, so that we can say that the L is a not regular. So L is a not regular. So this is about the pumping lemma concept theorem, and these are the conditions we need to follow for the division of the string into 3 parts. So, and how to perform this pumping lemma test for the given language, we'll see. And here the steps we have for the regular test the pumping lemma for the given language. So just we are talking about the regular pumping lemma for the regular languages, and what are the steps we need to follow for the pumping lemma test. And the steps to improve that the language is not regular using pumping lemma. So first one, we need to assume A as a regular. So if we are given the language is given, so this language is, we can first assume L or A is a regular. As a first step, what we have to do, we need to assume that A is a regular, and it has to pump a pumping length. So here in that language, we need to take the values as here. If it is having a power n, so this n is represented as a p, and this p it should be there in the language. So p it should be there in the language. So it has a it has a pumping length p, and all strings longer than p can be pumped. So here longer than p. So here as we already discussed, so this one, while dividing the string, while choosing the string from the language, given language, we need to follow this condition. So what it says that the length of a string. So the length of the string which is greater than or equal to p. Suppose here if you take p, value is equal to 3, and the length of the string is either 3 or 4 we have to take. And we need to pick that kind of string from the language. And the fourth step is now find a string. So find a string s in such a way that the length of, and first we need to choose the pumping length, and after that we need to find the one string from the language. And the fifth step, divide s into x, y, z. So here dividing the value x, s value, the string what we got. Suppose if you take a power n or b power n. So and here the n is n, instead of n we will write p is equal to p power a power p, b power p, and p is equal to 2. So then the length of the string is a b b a b, and here the length of the string is 4 here, and the length p is equal to 2. So 2, 4 greater than or equal to 2. So this condition is satisfying. So we need to pick this kind of string from the language. So here we are taking this string, and we need to divide this string into a 3 parts. So that is x, y, z. And next we need to show that we need to show that x, y power I, z which is not belongs to a. So for some I, so I value also we need to choose greater than or equal to 0. Then consider the how s can be divided into a x, y, z, and show that none of the above strings satisfy all the 3 pumping conditions and simultaneously, and cannot be pumped. So if cannot be pumped, we can say that it is a contradiction. So initially we assumed that the given language is a regular. So what we got the result, if it is not satisfying the condition, so that we can say that it is a contradiction. So contradiction means the what we assumed is wrong. So what we initially we assumed as a regular language is the language what we are, the input what we are taken for this test is a regular language, and what we got the result, if we got the result as a contradiction, we can say that the language is not a regular language. And this pumping lemma concept we will discuss with the example clearly. And here the example what we are taken for the pumping lemma. So here prove that the a power n and b power n greater than or equal to 0 and is not a regular. We need to prove that the given language, the language A which is having the length a power n, b power n greater than or equal to 0. And here we will follow the steps we need to we have learned about to prove this. So already we learned about the steps. So first we need to find out the string, and we need to divide that into three parts, and then we need to test for simultaneously we need to test for the three conditions. So that we can say that it is not a regular. So, and let us find the step by step process. Assume that A is a regular and has a pumping length P. So here we need to assume that A is having capital A is the language what we are taken, is having a pumping length. So that is also P. And let a string S is equal to A power P, B power P. Instead of N, we are taking it as a P. So pumping lemma. So we need to pump the values, so that we need to write the S is equal to A power P and B power P. So now divide the S into three parts, X, Y, Z. And to divide the S, let's make the value P is equal to 3. So here we are taking the value P is equal to 3. And so here after writing the S is equal to A power 3 and B power 3. So here the value is equal to triple A, triple B. So the length is obviously the length of the string is 6, and the P value is equal to 3. So this condition is satisfying. So we will take this string and we need to divide. So here S is equal to triple A, triple B. So S is in the first step we have chosen the S value according to the condition, this condition, and then we need to divide them into a X, Y, Z values. So let me take this, we'll divide equally into a X, Y and Z. And first step we need to follow the conditions like Y is greater than 0, and second one xy is greater than or equal to p, less than or equal to p, and x y power I z which is belongs to language or which is belongs to A. So these are the three conditions we need to follow. And while dividing the xy values, we need to y is 0 greater than 0. The y value is greater than 0. We will take A, single A or B. So AB combination we are taking. So AB value, so the length of y is equal to AB, and AB length is 2 and 2 is greater than 0. So this condition is satisfied. And then we need to check this condition. XY value less than or equal to P. So here X is equal to AA and Y is equal to AB, and this is the length 4 and this is less than or equal to P. So P is equal to less than or equal to 3. So this condition, is this satisfied? No. So we need to take the value like we'll divide according to this condition and then we will assume. So xy value. So y is obviously greater than 0, so that we will take only single value x and this y and this z. So here x is equal to, so xy value, so here xy value is equal to, so in the first condition, first division, we are not satisfied this condition, xy values condition. So that x is equal to now a and y is this is x and y is equal to a b, and this is also so greater than or equal to p, it is also not satisfied. So that I will take the value y value as a, so this one also not satisfied, and we will take this y value as a, so b. So here we will take the value y and this as a z, x, y, z. so that, so now it is satisfying. Let me check. So A, and this less than or equal to P, that is 3 less than or equal to 3. So this condition is satisfied. So this, according to the conditions, we are taking the values. So this condition is also satisfied. And then we need to check Ax, y power I, z, which is belongs to A. And the third condition is x. So x is equal to A and y is equal to. So what we have taken finally. So the y is equal to A power I and z is equal to B. And here, if you iterate or pumping length, so sorry, if you are repeating the value, y value, so we'll take the I is equal to 2. So here a power a 2 b. So if you repeat the values 2 times, so we'll get the result as a and B. And if you check the length of A and B, so here what we have to follow this. So triple A, so we don't have this kind of language, this kind of strings in the given language. So let me write this language in greater than 0. From 0 onwards we will take epsilon, and so if you take 1, n is equal to 1, we will read A, B, and n is equal to 2, A, B, and n is equal to 3, triple A, triple B, and so 4 A's, n is equal to 4A, 4 B's, and this is the language. So in this language we don't have this kind of string, so that we can say that this language which is not belongs to the language A. So finally what we got the result, so this condition is not satisfying, so that we have a contradiction. So initially we assumed that it is a regular language, so that we got the result. This condition is not satisfying in the sense, so this is a contradiction. So that the language which is given as a regular is a irregular or non-regular language. And one more example. So if you take a power n, b power 2n, so here let us assume we have this language which is having the pumping length p. So here according to the pumping length, so a power p and b power 2p. So here and the p value, will take this value as a 2. So p is equal to 2, and in that one we will find the language, the string. So the string is a if you take p value is equal to 2, a and b 2 power 2 is a 4 and b 4 times we need to write. So this is the language what we have taken, and here and first we need to find the string s which is greater than or equal to p. So this string length is 6 and less greater than or equal to 2. So this condition is satisfying, so that we will take this string. So s is equal to a b, and in this string we need to divide the value into a 3 parts. So s is equal to x, y, z, we need to divide. So and what are the conditions? So y mod of y greater than 0 and xy is less than or equal to p, and x, y power I and z which is not belongs to the language A. So these are the 3 conditions we need to follow. And here A or language L. And here we need to divide the xy values, xyz values, so that first condition is y value is greater than 0. So and also we need to check xy values when compared to 2 which is greater than a p. So p value should be greater. And here we need to divide x. So x is equal to let me write a b B, B, B. And here x is equal to A and B is equal to, we'll take, so y is equal to B and remaining we will take as a Z. And here first condition is, so y is greater than 0, not equal to, y is greater than 0. So that, so this one will type, so A and it is greater than 0, so this condition is satisfied. And xy, so xy, length of xy which is less than or equal to p, and this condition xy is equal to, we are taking a and which is greater than 2, less than 2, so 2 is equal to 2, so this condition also satisfied. And x power y power x y power I a z which is belongs to a, this is assumption and we will write, so and we need to repeat the value y, a y value, and so x is a and y we are taking a, and we will take I is equal to 2, so 2 we will take and b is equal to as it is. And here when we got the result a and b. So here it is a even, it is odd number and it is the even number. So this kind of strings, let me write the language first. So n greater than or equal to 1. Let me starts with a, b, and n is equal to 1 onwards we will start, and a, b, and triple a, and 2 into 3, 6, so 6 B's, and so on. So these are the language strings what we got from this language. And if you check, we don't have this kind of language, this kind of string, so that it is purely, it is not belongs to this, the string which is not belongs to the language. So this last step, last condition is not satisfied, that is nothing but we got the contradiction. So contradiction in the sense, initially we assumed the given language is not a regular language, we took as a regular language, and finally the result which is not belongs to the language. So that, so this is about the regular language pumping lemma concept. And we till now we discussed about the pumping lemma for the regular languages, and we also have the pumping lemma for the context free languages. The difference between these two is we need to divide the value, we divide the string into a, in regular languages we need to divide the string into a 3 parts, x y z, and now here we need to divide that into a 5 parts. So S is going to be divided into a 5 parts. Suppose here L is a context free grammar, so that same steps we need to follow, but the steps while dividing the string into a parts is different here in the context free languages. So here the language what we are taken as an input is the context free language, then there will be exist any integer. So here p what we are going to take is greater than or equal to 1 and also called as pumping length, such that every string, so every string s in the context free language which is the length of p or more than can be written as, so same concept what we while choosing the string from the language is what we are following the condition, the length of s is greater than or equal to p, we need to follow this here. And this s, the string which is divided into a 5 parts, and we need to follow these 3 steps. So here in regular languages only y value is going to be repeated, but here we need to repeat the 2 values here. So what are the 2 values? U, v and x values. If you divided the string into a 5 parts, those 5 parts, in that 5 parts we need to repeat the 2 values. Those values are v and x, and which is belongs to L, and the condition is same. and the length of Vx, and here we need to take the whatever we are iterating, whatever we are repeating the values, we need to take the length of two values which is greater than or equal to 1. And here, and Vwx, so Vwx, the middle part of the middle division of the length, it should be less than or equal to P. So same conditions here we need to follow. There we divided the string into three parts, and now here in the context-free grammar, context-free language, we divided the string into five parts, and we need to follow this five rules. Like we need to dividing the string into five parts. We need to check for these three conditions. And here entire pumping lemma concept for the theory of computation. So applying a pumping lemma will demonstrate some languages are irregular, and never utilize a language to demonstrate its regularity. So here, as we are discussing about the pumping lemma for the regular languages and context-free languages, so we are this pumping lemma test, which is used to represent the language which is not a regular, and with this test we can't say that it is a regular language. So it is a regular language, but it is undecidable. So it is a regular language. So if the result is pass, so the test result, the pumping lemma test result is pass, so we can say that it is a regular, but it is undecidable. Undecidable. And if it is fails, we can surely say that it is a unregular. And it is a surely decidable statement. So with this pumping lemma test, we can say that it is we can prove that it is a demonstrate its regularity. So we can't utilize it is a for never utilize the language to demonstrate its regularity. So pumping lemma is satisfied for if L is a regular, and pumping lemma is not regular if it does not satisfy the pumping lemma. So this statement what we have written is, if the pumping lemma is satisfied, we can say that it is a regular, and if it is not a regular, it does not satisfy the pumping lemma. And the limitation of pumping lemma is that it can only be used to show that the language is not a regular. So whatever the result what we got, based on the result, pass or fail, we can say that the given test result as a if it is a pass test, the result is the pumping lemma test is passed, so that we can say that the language is a regular, but it is undecidable. And the pumping lemma gives necessary information that must hold for language. So it gives the necessary information to hold for a language. Say A to be regular. And the pumping lemma is not a necessary property. So it is not a necessary property in all formal languages. So in all formal languages, it is not a necessary property. So particularly this property will not help to prove that it is a regular language. The pumping lemma provides the necessary conditions but not sufficient. So here with this statement, this pumping lemma is necessary, it provides the necessary conditions, but it is not a sufficient to prove that it is a regular language. And for language, it is for a language to be regular. The language like context free and context sensitive and context enumerable does not follow the pumping lemma. So all the languages we are not following this pumping lemma concept. So it's just a negative test. We can say that with this statement, with this test, we can say that it is not a regular language. The pumping lemma used for regular sets as a proof of irregularity of the languages. So particularly this pumping lemma test, which is used for the regular test to prove the irregularity of the language. The main reason to use this pumping lemma for the regular test is to show the limitations of regular languages. So mainly this pumping lemma concept, why we are using this pumping lemma concept is nothing but to show that how many limitations it is having, limitations of the regular languages. So what are the boundaries of the regular languages? So this pumping lemma concept, which says that it is a negative test, so which is going to be proven as a not a regular languages. And these are the references. And so pumping lemma is a negative test to test whether the language is a regular or not. And if you apply the language, for the given language, if you apply the pumping lemma test, we can get the results as a positive or negative. So in that one, if it is got the positive, so if it is satisfying all the conditions, the test results positive means if it is satisfying the three conditions, these three conditions, we can say that it is a regular, but it is surely it is not, it is a regular language, we can't say that. And if it is a fail, this any one of the condition is not satisfying, so that we can say that it is a decidedly we can say that it is a non-regular language. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.